work at Twitter on analytics type stuff, data science type stuff. And I'm going to talk about a little bit of my view on programming and its relationship to mathematics. Obviously, the topic there, the title says something about it. And then more specifically, talk about some of the code we've developed at Twitter for Hadoop and for some streaming applications, usually aggregations, and how we've used mathematics and how sometimes we weren't that uptight about it. So here's kind of an outline. I'm going to talk a little bit about my background and my view. Some of the things that we've done with abstractions that are like completely out of a math textbook, which we thought were really good. Some things that like were pain points that we just like we dealt with in less than ideal ways, and like what we look for, like what's the future of this? I'd like to hear some of, like maybe we have some other ideas. Maybe someone has some improvements we can make. So I'm really, my background actually, so I'm just kind of like, how did I wind up giving this talk? So I'm much more of a mathematician than a computer scientist. I was programming from a relatively young age. I only took one computer science class in school, and it was a language called Smalltalk, which some crazy people like, but I didn't really use much after. I did my PhD in quantum information theory. It was mostly what you might call mathematical physics, proving theorems about mostly the Schrodinger equation. That's all people are doing with that, which is just linear algebra. I was an assistant professor for a little while at the University of Florida. I did some stuff in quantum information theory there, but I started to move more interested. I was more interested in distributed computing, systems for that. In the academics are usually more interested in compute-bound problems. Since moving to Twitter, not quite 2 years ago, I've been more interested in the I/O-bound problems that you see in a lot of analytics. It wasn't really that into the functional programming community for very long. My introduction was I used Haskell for a computer-aided proof on an old quantum information theory result, and it was just a nice fit. You really could have done it in any programming language, but the idea was to use, get the program to enumerate all these possible little easy-to-prove results, which you could prove in your code right there. See that as long as the program terminated, they were each true, and then have it go through and enumerate billions of these. So don't listen to what the hell I'm going to say, because I've only been programming professionally for 2 years, So like, what the hell do I know about programming? Maybe it is math, but I'm going to make the case it's not, okay? So the first thing I want to say is the fact that a mathematical model exists for something is not equivalent to saying that it is that thing. And in my view, if that were true, everything's math. I'm not aware of anything that I'm skeptical that we can build mathematical models for. So I'm maybe saying tacitly that I'm like a strong atheist, like everything is physics at the bottom level, and maybe we just don't know all of it, but like there are mathematical models for everything, right? So I'm not saying that. But that doesn't mean it's math. So what is math? Well, actually, what do I think computer science is? What is programming? So I think programming has a lot more to do. I happen to choose the computer science building at MIT, but it has a lot more to do with building buildings. There's some craftsmanship there. There's some artistry. You're building a complex structure. Like, definitely, I assume the people who built that building know something about math. I don't think most mathematicians would say they were doing mathematics while they did that. They might have been doing some arithmetic. They're not doing mathematics. A lot of us might think this is dirty. When I'm enjoying programming the most, I feel like a craftsman. I'm there at the table, I'm making something beautiful. If it doesn't look beautiful, I'm not really as interested in it. Mathematicians will also say that, by the way. Like, beauty is very important to mathematics. But when I'm done making some code, it's like a chair I'm gonna enjoy sitting in. I'm gonna use this. It doesn't just go and sit in the library. It doesn't get written down in GitHub and hopefully never executed. Hopefully. When I'm programming, you're telling someone how to make something. That someone is often a computer. You're giving instructions. You're giving incredibly precise instructions. I don't believe when you're making recipes, you're doing mathematics. I think making recipes is fairly similar to what 90%, maybe more, of my colleagues at Twitter are doing. So it's like they don't recognize themselves as mathematicians. When they're there, some of them with their Ruby, and their other, like, I don't know, their hipster coffee script or something. That's not even like hipster anymore, right? I gotta go to like Roy, or I don't know what the hipster thing is now. But you're giving instructions. You're not proving theorems. You're not doing mathematics. And here's some programmers. There they are. They're following instructions, and hopefully that food tastes good. I don't know. So there's a great old joke about what a mathematician is, and it's a device for turning coffee into theorems. It sounds like a compiler to me, but it doesn't run on coffee. But so that's not what I do, though, really. I write code, and hopefully the compiler can help. So what are the generalizations that I'm kind of making here? I mean, like, one thing is there's this old joke about, like, the Supreme Court, like, how do you know pornography? When you read the old quote, it's actually, how can you tell hardcore pornography, which somehow makes it sound dirtier. Well, for obvious reasons, I guess. But the justice, I can't remember who it was, it's a very famous quote, but I know it when I see it, right? If I offered you $10 million to distinguish a mathematician doing mathematics from a programmer doing programming, I bet most of you wouldn't say that's controversial. Like, I will take that, yes, I will try to distinguish the mathematicians and get my $10 million. So generally, programmers are busy giving precise descriptions of how to transform input bits to output bits. They're writing down functions generally, in some sense, okay? Mathematicians get paid to prove theorems. If you're employed as a mathematician, the highest level, not to put too many judgments on it, you would hope to be like writing papers, submitting them to journals. They would just contain proofs. There'd be lemmas, you'd start with axioms. This would be your business, okay? That would be great. But that's not what programmers are doing. In some cases, compilers are doing that. But let's be honest, the proofs that compilers are doing are really stupid proofs. Like, it's like, if this thing over here is equal to that thing over there, and that thing over there is equal to that thing, then that thing is equal to that thing. I mean, that's like 10,000-year-old mathematics, It's like we barely got the compiler to do that. Like, let's not blow it out of proportion. So, now, that's not to say that there's nothing valuable from mathematics that we can leverage in doing, like, very beautiful code. So, we want to use abstractions from mathematics. And we want to have mathematical models of what we're doing. I hope there are mathematical models for the bridges I walk across. And we have some deeper trust than, like, I tried real hard to make a really great bridge, and it's not going to fall down, I promise. So mathematical abstractions and models are great. They're fantastic. So, like, some of the ones that everyone knows about, the mon asterisk d, duopoly, totally owning the category abstract algebra functional programming space. There are other ones. The semigroup turns out to be really awesome, just slightly weaker than the monoid. Abstractions over monads it seems like more monads than monoids, are really nice. You can see these like patterns where it's like I have this, any monad, and I'm going to do like this thing, and you have like a huge menu of operations that people didn't notice were all just like simple monad transformers. And that's really cool. Like, that's like not at all a bad thing. It doesn't necessarily make it mathematics, but it's like those are nice mathematical models. The other nice thing we get are the free proofs of correctness with some assumptions, which I'll talk about in a second, of certain things. So it's like, okay, I've got, dare I say, a bijection from type A to type B. And if I have some function from that is a reduced function, I care a lot about those reducers, that takes an A and a B and kicks out another A. Well, actually, no, I'm getting, Stephen told me this would happen. The next thing I'd be up here with these category theoretic diagrams. But anyways, I get these like free transforms from an existing function that I already have on hand to this other space that I want to use them when the transformation is obvious. And that turns out to be really practical. I'll talk about it more later. So when we're talking about mathematics, I keep saying this word theorems. So who proves the theorems? So it's not the case that the compiler is proving all the theorems in your code. When you write correct code, it's because you also at some stage proved some theorems, or like intuitively you thought they were true. In language like Clojure, you have like virtually no theorems being proved to you by the compiler. And so you resort to experimental. Like now they're experimentalists. They're not like theoreticians at all. That's what the tests are, right? We're doing some experiments. We're going to throw it into a checker. We're going to randomly run some experiments, see if our hypothesis is true. Keeps looking like it's true. I guess it probably is, Still no theorem there, right? That's just experimentalism. Okay. So we want the compiler to prove some theorems in Scala. That's great. As many as possible is good. And then there's this question of like how many are we going to hope that it will prove for us? Maybe all of them. So the question is how to manage the trade-off between things that like could in principle be proved by the compiler, but in practice are just a major pain in the ass. Like Clojure developers are happy all day doing their stuff, and like, you know, for the most part, they seem to love it, you know. I guess it's cool. But the compiler's not doing any work for them, and they can build fine systems. I guess there's no real evidence that the stuff that they're building is worse than what we're doing. I don't think there's evidence at all for that. It would be great if there were evidence and we'd just do something better. So what were some of the wins? What were some of the concrete things that we did? So we released this library, Algebird. It was actually a fork of just some code that was sitting around in Scalding, which is a Hadoop library that we use, which is like, it started as kind of like a Scala DSL of cascading, and then we tried to make it as more and more more as close as possible to the Scala Collections API. Along the way, we wanted to do some linear algebra. Why? Because a lot of the things at Twitter are linear algebraic. If you think about, we have a graph of people interacting with tweets, we have a graph of people following other people, and so a lot of these things are linear algebraic. So if you want to do some kind of feature extraction, to do any kind of modeling of this, it's really nice to think, okay, I'm just going to take this vector and hit it with this matrix, but actually doing that kind of calculation on Hadoop can be really ugly. Like if it was your job to write those as like Java MapReduce, like you've got more patience than me or you quit your job. Like it's not something you'd really want to do with your life. So the question was, what should the elements of our matrices be? And so there was like, oh, maybe a long, maybe a double, and it's like, meanwhile, like, it's like, hopefully we get to the answer soon, but like, let me talk you out of a long or double, and like, let's just do like either a monoid, ring, or group, depending on the context. If we're gonna just add two matrices, we just need the monoid. Why do we need the monoid even rather than the semigroup? Well, these are huge matrices, so they're sparse, and most of the values are 0. So it didn't even occur to us to start with a semigroup because like we already knew from the get-go that we were always going to be dealing with sparse matrices. So the 0 was like really, front and center. The ring is necessary to do matrix multiplication. We heard a little, there's a great library, Spire, which if it existed when we were doing this, didn't know about it, and we'll probably take their type classes. It looks really awesome. We had this question, what interesting rings are there other than numbers? So there are a few that you can think of, polynomials, et cetera. I actually don't multiply polynomials in the follower graph or anything, but like I maybe lie about it just to make it sound like cool because we like doing algebra. But anyway, so that's the background. And so we came up with something like this. So cosine similarity, which is a measure, if I want to recommend, like you might be interested in following some person A or B, it's a really simple, totally brain dead algorithm that you can run, and it becomes really simple now. We take a TSV, we read it, we say that it's a matrix of row type int, column type int, and value type double, and we can just say code like this where we're going to, like, let's L2 normalize it, so each of the rows becomes unit length. And then we just transpose and multiply them together and write it back out. Now, if you were to write this job, that's there's no way you can finish that in like a 1-hour interview in Java, like at the board, like it would be a disaster. Like someone could not write this code. And more to the point, every time you keep doing matrix multiplication, there's a good chance you're going to get it wrong. So there's a big win in us saying that's a matrix, you're multiplying it, like let's just use this code. We stop having errors. But then the question, like there's this nagging issue, like, well, what if it's not, like, so if you went to the Spire talk and if you know a lot of algebra, it's like, well, there are a lot, like, what if it's not a ring? What if it's a rung? What if it's a rig? What if there's no negation? You're not really ever using negation in multiplication. Should it be a rig? You go down this giant rabbit hole. When I say programming in math isn't math, I'm saying I don't want to go down that rabbit hole. I want to do some other things. Rings are awesome. I'll stop there. So let's see some of the value. So here's an interesting calculation we could do super easily once we had like a monoid on some like interesting data structure. So the question is the following. For each user, compute the set or the size of their followers' followers. So you guys are all hugely important people. You must have tens of thousands of followers on the Twitters. The average is actually like 1,000. So don't feel bad, like if you have less than that. It's because like you got Obama and Lady Gaga, and you have the skew. You have this distribution that has a super heavy tail. Again, by the way, it's interesting. Is that mathematics or is only category theory mathematics? But anyways, I'll let you think about that. For statistics, there's also statistics in the world now. It doesn't come up much. Anyways, so because of this heavy skew, when you do this count 2 hops out, it becomes extremely expensive. So a naive algorithm will be expensive. But what is that naive algorithm? So in this case, here's a directed graph. We're concerned with the second followers of A. By this, in this case, I mean the set E and F. No big deal. I'm going to move a little fast. So once we have this abstraction that we don't think of it in a database or joins, we're just going to think the follower graph is on the left. I've just represented this graph over here as a binary matrix. And every step on the graph is hitting some vector with that matrix. And if I go 2 steps, I'm just hitting it twice. So I see the second power of that matrix. And what are the values of this vector? Well, I need to have a monoid. That was my constraint. I need to have a monoid on what I'm going to propagate with. So I can easily propagate any, because propagation I'm just summing. I don't really even need the monoid. I actually only need the semigroup. But well, it's the sparse matrix. You see all the zeros in there? So I wanted the monoid. So in this case, for the vector, I put everyone's set with themselves. So A starts with the set of only himself. His 0th followers are himself. He is his own 0th follower. And now once I propagate twice, I'll get the answer. I'll show the code in a second. Now, before we look at the code, what if we didn't know math? Math is awesome. It's great to know math, because if you didn't know math, this would just look like a join. Okay, you'd have this it would be 2 joins, and then you do some aggregate count and everything. And no one does I don't know, no one. Are there version control things for SQL and everything? It's always just a nightmare when you see this stuff. And there's no abstraction that I ever really see in that. That's my bias, obviously, but that's my experience. So you have all this opaque code that hides the structure of what's going on, when the structure is actually super simple. Like the cosine similarity, it's 2 lines. It's nothing. So it's great to know math. So here's an implementation of this if we weren't doing it in Scalding. But the point is, this is a very nice map reduce job. There's this microphone here. Usually I like to wave my hands all around and run all around. But if I take the microphone out, I'm not going to be able to put it in. I'm being vulnerable with you people. I'm sharing my anxieties, you see. So first we do a group by. We're grouping by all the incoming edges. So everyone who's coming to me or to you, we're going to group by that. We're going to shove over all of the values v. We get passed in, you get this vector. I use a map here as a vector here. It's a sparse vector, if you like. Once I get all those values, I'm just going to sum them all up. So I either get the value or I get this 0 out for that item you see. You don't have to pay too much attention, but I'm summing. This code works for any monoid, and it's great. It's great that it's abstract in that way. And you could actually run this and play with it, and here's an example. Obviously, we don't care about graphs that small. So the exact problem becomes too expensive because Obama's second followers are huge in number. Bieber's second followers, it sounds there wouldn't be that many of them. But if you go to the top 5,000 most followed people, all of those people are followed by a lot of people, and they become a huge cost to do this kind of algorithm. So one approach to do is to do approximation techniques. So one thing you could do, if you know approximation techniques like this, like hashing techniques, hyperlog turns out to be a monoid. If you don't know that, it's easy to see. Hyperlog is an approximate cardinality estimation. I want to see how many unique items have I seen. That's kind of how many unique second followers. How does it work? Well, it winds up working by doing hashing, a bunch of different hashes, and then keeping some minimums along the way. But minimum is totally a monoid, right? So I take the maximum possible value. That's my 0. Minimum, clearly associative, you're done. So to get a feel for how minimum works to give you an approximate set size, you see that we take each value and we hash it from the interval 0 to 1. So real numbers in there, or a bunch of bits if you have more of a computer science background. And then you just keep the minimum value. Finally, after you've done this n times, that minimum value, the expected value that it will take will be 1 over n, where n is the number of unique items you've seen. So if you just take the inverse of that, you've got n. Sounds pretty good. Actually, the variance of that method is too high, so you do various corrections to that, and that's hyperlog. So we could do this exact same code where instead of initializing that vector with each set of like just the set of themselves, we take a hyperlog-log data structure, which you can see in the Algebird project, and a couple of other nice aggregation monoids for like streaming or large-scale aggregation. And now we've got these data structures, and we propagate those through the graph. And those are a fixed size. They don't grow as you've seen more. So with like about a 16 kilobyte, which is still kind of large, data structure, you can get like less than 1% error. And no one really cares. You know, that's fine, 1% error. And you care about ranking problems. So you're talking about the top K. They're not even within 1% of each other. So you're still going to get the rank right. So if it's your job to get the top like 500 followers, like probably none of them are within 1% of each other. So this just works, and then I just ran it, and it's a couple lines of code, and then I get this interesting answer right away. So it's a huge value. The answer, by the way, is Obama. He's not the most followed or the second followed or even the third followed, but I don't exactly know why he's the most second followed. I assume it's because there's a high variety of people who follow Obama, whereas some of the other people are more focused. Like if you follow Bieber, it's like you have a really, like it says a lot about your interest. But if you follow Obama, it's like, you're an American, or like not even American, you're just somewhat interested in the president, so yeah. So what was another win? So Semigroups turned out to be a huge win for us recently. There's another project that we've been working on to do real-time aggregations. And in this project, what we do is, so Hadoop is nailed like the reliability picture. So batching and getting that reliable data produced on your Hadoop cluster, like it works great. But serving that data is painful. Like you can't serve out of HDFS, so you have to think of a different story there. And just the time to get it into a serving infrastructure due to queuing delays in your Hadoop cluster are non-trivial. So how do you work around this? So our solution is we tee the logs off. Once we're going to write it onto the Hadoop cluster, and then once we're going to feed it through, say, Storm. You can build a system on Akka, whatever you like. Now we want that real-time system, that's the thing at the top, the RT with the pentagon. Not pentagram. Different thing. We're not into that kind of stuff. I don't know, it's okay if you are, whatever. Anyway, so we tee these things off, and now the nice thing is in real time you have all kinds of problems. Maybe you have loss, maybe you have like queues backing up and we don't want to have infinite memory, so we're just going to throw things away. But it's really easy to get, or you have duplicated messages, like Storm has at least once semantics, not like at most once by default. You can use some slower transactional mode, whatever. So our idea was like, look, let's just do a noisy real time in some small batching. And you see there's no edges out of those real-time buckets. Only edges come out of the Hadoop. So Hadoop, see now I'm going to do the thing. Okay, so Hadoop gets the log data, and it keeps feeding forward. And what are we doing? We're just doing a semigroup. We're summing all the way up. So we're summing it, like for each key, we're going to sum all the values for all time. That's what this system's trying to do. And then when we want the real-time data, we just look up the most recent batch that we don't have online. So we'll push these Hadoop batches into some write once, like servable data structure, but it'll be a few hours behind, maybe an hour, maybe 15 minutes, who knows, it's a systems problem, but it won't be a millisecond behind, okay? And then we'll look over to this bounded size, and more importantly, bounded error, real-time read-write thing. Maybe it's a memcache store, okay? So that one, and because we have associativity, we have a semigroup, we know that when we look up the most recent batch we've got and we add in the real-time batch, we know that we've got the right value. It's great. So that was a win. And then I got this bad reputation. There's someone tweeted monoids or so last year, where I was going around Twitter saying like, okay, you tell me a problem, I bet it's a monoid. It's actually like amazing. Most aggregation problems in streaming algorithms are actually monoids, because otherwise they're just like not an efficient representation of the problem. So most of the things that we are aggregating, they're almost all monoids. It's really interesting. So the facts on the ground are that we're developing code to be used by hopefully hundreds of engineers at Twitter. It's not a monolithic structure, so if they don't like your code, they're just like, okay, I'm not going to use it. So I care about that. I care about having internal adoption. That matters to me. Some of those users use Java. So like totally going off the deep end in all sorts of super ugly areas of Scala that look like horrific when you try to call them in Java is something I'm trying to avoid a little bit. Not completely, but usually trying to avoid that. Some people program Scala as if it were Java. So they just like fire it up and it's like it's Java with type inference. And those people are on the payroll, and like that's fine, that's okay. Like not everybody has to code the same way, you know? So where do we go wrong? Where do we make some mistakes? So here's I'm going to talk about some of the ugly stuff. That was the decent stuff. So this stuff's not perfect. Even if you say it's math, it's not. You're lying to yourself. I love the math. I love it. But who proves that your monad is a monad? You're coding up your Haskell, your implements your bind, but it's not bind. It's not associative. It's doing crazy stuff. Compiler won't tell you that. You have to prove a theorem. So, and like that happens all the time. What if you just what if you return error everywhere? What do we do? I don't know. I don't know what we do. So same thing with the monolith. So who proves your bijection is injective and surjective? And what about runtime exceptions? They're not going anywhere. You're going to get out of memory. You're going to get you're going to call some library and they're going to throw some runtime exception you didn't know they were going to call. You have to deal with it. I don't remember any of that from any of my real analysis classes or anything. That does not seem at all like mathematics to me. So our approach is, look, we write some laws we want our code to follow, we write some Scala check for it, and we chillax. Don't worry about it. It's not like that big a deal, man. So here's where we ignore the rules, just jam out code, and actually the house does not burn down. You know, it's like okay, you know. So here's our ring. Oh my God! You threw an error. Where's your unit on the ring? Oh my God! Guess what? We never call that method. It has never caused a runtime exception. And I didn't want to like totally geek out on like massive type hierarchies. And like it, you know, it wasn't a giant mistake, you know? No one was harmed. Okay? So there are ways around this, and the Spire guys, they did invest in this, and that's great. And maybe we'll adopt their work, but I had other things to do at the time. So, but the other thing to keep in mind here is if I give you a ring without identity and I pay you $1 million to give me a ring with identity, you can do it. Just like if I give you a semigroup and I pay you $1 million to give me a monoid. You extend it with a fake like zero value, like you lift it into an option, like you have the none now, that's your zero, and you go on with your life. If programming is math, by the way, we know that. And we don't like totally obsess. Like, yeah, we know there's an equivalence between semigroups and monoids, not a big deal, you know? Same thing here. It's trivial to extend like a rung to a ring, no big deal. So the sad part is, usually people complain about this. We even sometimes, if you would believe it, get people commenting like on these giant issue threads. But so seldom do we get the pull request. Please, just give me the pull request. We'll take the code. Okay. Now, how about this amazing function? Crazy useful. You use it all the time. Anyone intuitively, obviously, can see that there's something wrong here, okay? But you do it in your code all the time. So where you put it in, I don't know. Oh my God, wait a second. Not all possible byte arrays are exactly length 4. This is not truly a bijection. It's super useful though. Are there better solutions? Yeah, there are. So here's one better solution. So here's a bijection between array of bytes and gzip bytes. This is a bijection. No one can doubt that. How do we implement this though? We do the normal thing, just do some compression, and then we wrap up the array that we get in the end with this decorator class that says, look, I promise it's gzip bytes. Now, if this were closure, there'd be no types anywhere, and it wouldn't matter at all, right? But it'd still be a bijection. Mathematically, it's still a bijection, right? The types didn't make it a bijection, did it? I don't think you can make that argument. And the invert just takes them off. That's one solution. That's in the code. That was one solution we took. I don't want to decorate every array with this thing. Another solution, I've never met him in life. I've only met him on the Twitters and GitHub. I think his name's Jed. Maybe he's in the audience. Maybe he's not. But anyways, Jed suggested this. I think it's a hack taken from Scala Z, which you define this type at, which just takes your type T and extends it with this thing called tagged. And then you can say that you have a bijection between ints and strings, which of course exists. All the 32-bit integers have one canonical representation of strings and back and forth, okay? Totally clear. And then you just decorate this type and say that you're good. This is kind of ugly too. What's the downside? Well, like, it doesn't seem to work with primitives. So if you decorate like int at something, That seems that the Scala compiler can't handle that. And also that @@ is totally stripped off in Java, and I kind of care about that. So that sucks. Here's another solution I'm playing with a little bit. So let's get more strict, back to the mathematics. Some things are bijections, some of these things are injections. On the invert, we go to an option of A. We can't always invert. Okay, this sounds pretty good, okay? But now here's the problem. The Scala compiler can't deal, there's this nice connection between all bijections are injections, and all injections are bijections over that restricted subset. This theorem has a name. It's the Cantor-Schroeder, someone else theorem. Totally obvious. Work with people who've never taken a lick of math, and they totally get it. But Cantor can Cantor needs that for his ego. We can name that theorem after him. No big deal. But the Scala compiler has a lot of issues with this. You've got these now recursive implicit types that you're pulling in. Injections can take an implicit bijection to construct them, and then you're doing the low priority pattern with some low priority injections coming into play, and it's like compiler sometimes deadlocks, sometimes seems to run forever, don't really know. I don't really want to deal with that, don't really want to debug that. And unfortunately, and kind of fortunately, I'm not paid to debug that. So I've got to make some expedient choices. And the last thing I want to, if this were closure, we wouldn't really be that worried about it. So I think that we should leverage the type system for what it is. So we have these great mathematical models, and they're awesome. And we use them, and they're powerful. We get a lot of benefit out of them. But there's a certain, I'll stop there. We need to remember that humans can and must prove the theorems, though. The computer's not doing that for you. And if you can prove the theorem without the type system, is that okay? I think that's allowed. I think that's necessary, okay? So even if the compiler can't see something, sometimes we say it's true and we just go forward. I bet almost all of us have as instance of somewhere in our code. And you might say something like, this is okay because I can prove that this cast will never fail. Or if we like statistics, we'll say it will fail sufficiently infrequently that I'm satisfied with it. And that's still math, it's statistics. So I'm supposed to say this, please come help me improve scalding, make it faster, work at Twitter. Get called names for not knowing mathematics. That's my pitch. Thanks.